Alright, hello. This is my video for calculate step number 8 for our project we've been working on. So this is the last step for this project. And overall I have to say it's been a pretty interesting project. I like how it's been more hands-on than other parts of the class where we actually get to collect data and create a wind tunnel and then use that data along with the things that we've learned in chapters 11 and 12 to calculate things like in this step here where we're actually calculating the terminal velocity of those different shapes and how much percentage of that terminal velocity will be at different times or distances. And so that was kind of what this step was about. So that was pretty interesting. But for this assignment, our group's been communicating quite a bit. It's been me and Dylan Kitchens have been communicating together, and we've been kind of talking back and forth and kind of comparing our results and our thoughts on how to go about solving these problems. And then we've also been discussing kind of what we learned from it and what we thought was interesting and kind of how we interpreted the results that we were getting. And so we were also communicating with the group Careless Droids, which is Daryl Light's group and the people in his group. And so we created a discussion in the Canvas website for our class that was Careless Droids and Banana Engineers, and then we were able to post in there and then once again kind of compare our results on what we were finding as well as kind of what we were interpreting from them and what was interesting. But for this assignment, for calculate step number 8, we were supposed to use the equations that we found in part number 7 to answer the parts of calculate step 8. And so I decided to use MATLAB after we finished talking together on Zoom, because I agree that it will help us to be more accurate with our integrations because we don't have the round-off errors as bad, and it keeps us more organized. And with a lot of the integrations that we were doing, we were able to just have different equations for each of the percentages that we were looking for, and so it made it go a lot quicker. But the first part of this I actually did a little bit out of order because it just worked out better so I could use it in the next calculations. But so I retyped the equations that we found in part number 7, and so these are the linear equations for each of those shapes. And then using that, we know that once you reach terminal velocity, your acceleration has to be 0, and so I kind of drew that here with a little free body diagram to help me think it through. So here's those equations once again that I wrote out, and we can see on the free body diagram of the golf ball or the sphere that we have drag force going up and the weight mg pulling us down. And so once we reach terminal velocity, the velocity won't be changing, our acceleration will be 0, and those forces must be equal. And so I kind of did it by hand for the golf ball to start with to kind of get an idea of how it would go, and then I used MATLAB to complete that for all of the other shapes. And so what we have here is the force going up minus mg, so that's the sum of the forces, and that has to equal the 0 acceleration. And so here is part C on MATLAB. I have each of the 6 different shapes, and then to solve this I decided to use symbolic variables. It's just a little easier for me. I'm more comfortable with that, and the integration was a little bit easier for me. And so I set some variables up here using symbolic for v and t, and then I set g as our constant for gravity. And then what I did here was I just used the solve command and typed it in similar to my work here that I have on the paper, and then I also put in double so it would convert it back from symbolic back into a number that was a little easier to understand. And so then I just put solve in and designated the variable that I wanted it to solve for, which in our case is v, which is the terminal velocity of each of these shapes. And so if I scroll up here, we can see that these are the terminal velocities that were calculated for each of those shapes from MATLAB. And then we could kind of use that in other parts as we wanted to calculate the when it reaches 50% of the terminal velocity and things like that. And so the next part I did was part A. And in part A, we were asked to use the functions from part 7, which are up above, to create an integral equation to determine the time at different percentages of the terminal velocity. And so here's the work on paper that I did for that. And so we're using this equation here, which is acceleration we know has to equal dv dt. And then we were able to use some of the tools that we learned in chapter 11 to solve the differential equation. And so we move the variables to the correct sides, and then we have this integration here. And so doing the same thing in MATLAB, I have the variables here for each of them, and then I use the int command to integrate. And looking at the format for how we rearranged it, we know it has to be 1 over our acceleration equation, which is mass times acceleration. So that's why I put the masses in as well. And then running that, we're able to get a general equation. And I decided to suppress those because since I was in symbolic method, it was kind of hard to understand because it left everything with fractions and things like that. But I was able to use that for part D. And so this is the work for part D here. And part D wanted us to use our results from A and C, so the terminal velocities that we calculated and those equations that we found. And we were going to use those to find the time to reach 50%, 90%, and 99% of the terminal velocity for each of the shapes. And so this is one instance where I was glad I was using MATLAB, because this is a lot of integration. It even took me a long time to type all of it in, but with MATLAB I know it was more accurate and more organized than I could have been by hand. And so what I did here is I kind of grouped them in groups of 3, so each shape here is labeled for each of those 3 different times, and then I took my terminal velocity and multiplied it by whatever the fraction is that we're looking for, so either 50%, 90%, or 99%, and then just substituted that into the integration that we found in part A. And so running all of those calculations, I can just show you here. So these are some of the times for the ball to reach, or the shape, I guess, to reach that velocity percentage. And so, for example, here's the golf ball, and so this is the time it would take to reach basically 99% of the terminal velocity. And after talking to you, you kind of explained to me that we couldn't actually use 100% because it blows up our differential equation if we plug in 100%, and so that's why we had to use the 99% that you specified in the instructions for this part. And then part D was, part B and D, I guess, are related, and they were similar, except we were using this equation here because we wanted to know the position instead of the time. And so similarly, we had to rearrange that equation by solving the differential equation, and then I kind of did that on paper again, and then used MATLAB once again to solve that. And so this is similar to part A, except I've just changed the time here, t, to a d for distance, and then I had to modify the integration a bit to match this formula that I showed right here. So there's an extra v that we had to account for. And so running those equations, here are some of the, let me get to the next section. So these are the values for time for each of the different shapes, and then these are the values for distance at each of the different percentages of velocity. And so this is part E here that I'm showing now, all of these values. And then once again, similar to part B, I just typed all this up again and labeled either 99%, 90%, or 50%, and then once again used double to convert it into the number that's a little easier to understand. And so this is a kind of a similar process to the other one, except we're looking for distance instead of time. And so overall, I'd say it was pretty interesting to compare the different distances and times for the different shapes. Some had a higher terminal velocity than others by more than I expected. Some shapes, the shape actually had a bigger impact than I thought it would on a lot of them. But it was pretty cool to be able to see that, and MATLAB did a really good job of putting all of the final information in a way that was easy to kind of scroll through and see what the results were for each of those. And so over this project, we were able to really see how the things that we're learning is applicable to actual experimentation and things of that nature that we were working on. And so that's all I have for calculate step 8. So thanks for watching. Bye.